Okay, so welcome to everyone. Nice to see you again for this seminar of the High Energy and Cosmology series of EAIFR seminars. Today we are having Professor Aseem Paranjape from IUCA, the Inter-University Center for Astronomy and Astrophysics in Pune, in India. Aseem is an expert of large-scale structure, and now he's dedicating a lot of effort to understanding the um, the effect of cosmic tides on the formation of large-scale structures. So this is what he will tell us about today. So Aseem was a postdoc at ICTP in Trieste some time back. This is actually where we met. And after that, he moved to Zurich, right, to ETH for another postdoc. And I think then after that, he just got a faculty position at IUCA. Is that right?
That's right.
Yeah. So here he is today. So thank you very much. Now I leave it to you. I will remove my video and it will be all yours.
Thanks,
Thank you,
Marcello,
Aseem.
for the very kind introduction and for the invitation to give this talk. So,
Oh,
what
yeah,
I will
sorry.
do,
Sorry, I
yeah,
forgot. Yeah, I forgot to tell everyone. So we are, Aseem is fine with taking questions anytime. So perhaps you can either write it in the chat and
so I
and
think
I,
it's easier for me if someone raises their hand, and Marcello, you can unmute them
yeah, okay.
because I will not be monitoring the chat.
Exactly, exactly. So otherwise, we will also take questions at the end. If they are not urgent, we can just wait for the end of the talk, and then
Yeah.
there will be a round of questions. There are not so many participants, so there will be chances for everyone. Okay, let us start. Thank you, Aseem.
Okay. Thanks, Marcello. Okay, so what I thought I would do, so I had asked Marcello what kind of audience to expect, and I guess not everyone is an expert in structure formation and cosmology. So I planned the talk to be sort of a general introduction for most of the discussion, about half of it, after which I will focus on some of the things I'm personally working on. And it's not a review as such of the field, so I've not really been very enthusiastic about citing everyone in the literature. So if there are experts in the audience, you will please forgive me if I haven't cited your favorite paper or your own paper or something like that. And like Marcello said, please feel free to jump in and ask questions if something is not clear. So I work at IUCA, that's the Inter-University Center for Astronomy and Astrophysics in India, in Pune, in the city of Pune. And if you've never been here, this is a glimpse of what it looks like. This is a stock photo from our website. This is a photo that I actually took. So this is the main campus. This is the recreation center in the residential area where I live. And it is actually as beautiful as you see it here. So I welcome you as soon as this entire COVID stuff is over. Please, if you are interested in visiting us, we are very welcome to visitors. In fact, we are an inter-university center. Not unlike the ICTP, our mandate is to promote the spread of astronomy in particular in Indian universities. So we have associates from Indian universities who come and visit us, etc. And we are, of course, open to having visitors from outside as well. So what I will do today is to talk about cosmic tides and their role in the formation of large-scale structure. I will explain these terms as we go along. And this work is done in collaboration with the people you see here. Oliver Hahn is right now a faculty. He's in transit between France and Austria. I overlapped with him as a postdoc at ETH. Ravi Sheth was my postdoc supervisor at ETH. He is currently at ICTP, I'm sorry, and he's currently at UPenn. Sujata Ramakrishnan is a PhD student working with me here at IUCA. and Yolanta Zupa is a postdoc in Nice in France. Okay, so let's get started. So broadly, what I will do is spend some time talking about the notion of what is called hierarchical structure formation, and in particular, the quantity of interest for us today, which is the cosmic web. And the idea here is that this quantity called the cosmic web provides the environment in which things like galaxies or dark matter halos, as I will explain as we go along. So these are tracers of the cosmic environment. And so we want to see how the cosmic web shapes the growth and evolution of such tracers. Okay, this is broadly the theme. So all of these are actually interconnected, and I've just arbitrarily separated them just to guide the discussion. So this is what I want to do today. And I will talk about, as we go along, some recent results in this context. So just up front, this is what the cosmic web looks like. So it is by now a well-established fact that if you point telescopes around you, you will see that the universe on very large scales, these are scales of tens to hundreds of megaparsecs in length away from you. At these scales, the universe has a distribution of matter. Matter is primarily locked up into galaxies. And these galaxies are distributed in space in the manner that you see here. So the radial axis you can think of as the distance away from you. It is measured in units called redshift. Redshift is an observable quantity that you measure from the spectrum of a galaxy. This is very similar to a Doppler shift that you have, that people may have come across in undergrad. And in cosmology, because of the expansion of the universe, the spectrum of an object gives you a redshift, which can be tied in a very clean manner to how far away this object is from you. So this axis is like distance away from you. And the other direction is an angle in the sky. And the second angle in the sky has been collapsed just so that I can show the plot on 2 dimensions. And what you see here is that galaxies in space around you are not randomly distributed. They form this network where you see places where there are lots of objects. Every point on this graph is a galaxy, every black point. So there are places where there are lots of galaxies. There are places where there are no galaxies. And you can see that the distribution of these galaxies is organized into this filamentary network. There are filaments which meet in nodes surrounding voids where there is nothing. So this picture of the universe around us, this is called the cosmic web because it resembles the web of a spider. And this has been around for a long time now. The first such surveys were very tiny on this scale. The very first surveys would have taken up a space which is just where my cursor is pointing just now. And as time has gone along, we have pointed bigger and bigger telescopes at the sky and looked longer and longer. So we have seen further and further away. And this is the kind of picture that has emerged. So this particular image is from the 2-degree field galaxy redshift survey, the 2D GRS, 2DF GRS, which was one of the first surveys to provide statistically significant volumes in the universe using which we could constrain cosmological parameters for the first time using large-scale structure alone. Until then, it was CMB which had been dominating. The cosmic microwave background had been dominating cosmology. This was a game changer in the field. And on the right, you see more or less the current state of the art, which combines images from the Sloan Digital Sky Survey, the SDSS, and another survey called Vipers. So this particular image is from the Vipers paper by Gigi Guzzo and company from 2013, so already somewhat old. And here you see that this kind of large-scale structure that was restricted in this image to redshifts of 0.2. Think of this as a linear length scale. I will show you another version. Oh, you actually have it here. So this redshift of 0.2 is something like of the order of 600 MPC away from you. Okay, 600 megaparsecs. So this earlier image was restricted to around 600 megaparsecs. And now you can see that this axis is going out to a couple of thousand megaparsecs. And the point is that this large scale structure is still there in the universe. It is not that as you go further away, it disappears, or as you go further back in time, because redshift is also time, because of the finite speed of light. So the large scale structure has been there for a while. It is there far away from you. It is also there close to you. And it looks pretty similar, yeah, filamentary pattern, etc. So this slide shows a zoom in of these two Vipers fields, a little bit from here and a little bit from here. Okay. And what you see that in detail, there is some very interesting, interesting stuff happening. For example, look at this part. This is something, when I first heard this talk by Gigi Guzzo, this is exactly the object that he emphasized. And I think it is a very nice object to emphasize. The object that you're seeing is the lack of galaxies. Okay, so every point is a galaxy. And in this region, you see absolutely nothing, right? This is completely white. And this is not because the telescope was not able to observe for some reason. The telescope has observed. In fact, it has observed galaxies here as well, which are further away and therefore fainter, right? So there is no problem with observing these galaxies here. This is a physical underdensity of the galaxy number here. And now just to get a sense of scale, look at the axis here, right? So this stick to this stick is 100 megaparsec. So this end-to-end diameter is something like 30 to 40 megaparsec. So this is a huge void, which has absolutely nothing down to the depth which was observed, depth in faintness, which was observed by Vipers. And it's a huge void sitting there. Yeah? So these kind of fascinating structures are prevalent everywhere in the large scale structure around us. And one of the most interesting questions for me doing cosmology is to understand how this large scale structure has come about. So of course, this is not that people are asking this question for the first time. This is a very, very well studied field going back several decades, at least 50 years. And what I will do is to discuss the phenomenology of the cosmic web and the dynamics of the cosmic web in the framework of what one can call the standard model of cosmology. So I think this should be familiar to most people. In the standard model of cosmology, we believe that the universe is dominated by an unknown dark component, which is very close to being a cosmological constant. Among the other fractional energy budget, the dominant part is taken up by cold dark matter. So there is dark matter in the universe, and we believe it is cold and collisionless. It is dark in the sense that we can't see it, but we can infer its presence based on its gravitational influence on other stuff and on the light that we see. Okay, so I will not go into a discussion of evidence for cold dark matter and dark energy. Please feel free to ask if you have questions later. The stuff that we are made of, protons, neutrons, electrons, etc., are called baryons by cosmologists. We club everything together as baryons. We don't distinguish baryons and other particle physics species. And these baryons comprise a relatively small fraction of the total energy budget, approximately 4 to 5% or so. There is radiation with which we probe the universe. Of course, there is now also gravitational radiation, but here I'm talking about ordinary radiation that we are familiar with. This is such a tiny fraction that I cannot plot it on this kind of plot. It is something like 10 to the minus 4 of the current energy budget. These days, people are also interested in the effect of massive neutrinos. We know that neutrinos have mass, and people are interested in asking what effect does this have on the evolution of large scale structure. So there is interesting physics there, which I will not touch upon today. So this is the broad framework in which we discuss things. So what the structure formation that I'm talking about primarily happens in the cold dark matter, and whatever happens here primarily drives what happens to the baryons at large scales. Okay, at small scales, things are different because baryons have pressure and they have a different physics than cold dark matter. And at small scales, the densities of baryons start dominating, and then there is gas physics and gas temperature, etc., that we have to account for. So we are not discussing those scales immediately. We are focusing on relatively large scales where the primary species driving structure formation is cold dark matter. Dark energy mostly plays a role only in determining the overall expansion of the universe and the effect it has on slowing down the formation of structure. So as you know, the presence of the cosmological constant accelerates the expansion of the late time universe. And this has the main effect of slowing down structure formation a little bit. So that's the biggest effect of dark energy as far as we are concerned. All right. So in this framework, the current understanding says that initially at very early times, approximately, let's say 400,000 years after the Big Bang, the universe was in a state which we can currently observe using the temperature anisotropies of the cosmic microwave background. So this is one of the key observables in modern cosmology. It is a relic radiation that was released around this time after the Big Bang. And it has a nearly black body spectrum, which has a slightly different temperature in different parts of the sky. So it's basically the same temperature, 2.725 Kelvin, everywhere in the sky, with tiny fluctuations. Okay, so there are some fluctuations of the order of 10 to the minus 3, which are due to our local motion. Once you remove those, what is left are very tiny fluctuations of the order of 10 parts per million. And these are believed to be a remnant of primordial fluctuations, which formed the seeds of the current large-scale structure that we see. So what does this idea say? It says that give me initial conditions which had even tiny fluctuations, and then allow these fluctuations in the matter to grow under the influence of gravitation. Because gravitation leads to an instability in perturbations. Because if I have a region of space like this red part, which is slightly overdense compared to its surroundings, then this overdense region will tend to pull in matter towards it and become even more overdense. And now it's more overdense, so it gets to pull in more matter because it's stronger. So this is an example of the rich getting richer, and correspondingly the underdense regions become progressively more and more underdense. So this is the hallmark of instability in the system. I have perturbed the system initially, and there is a runaway instability where overdense regions become more overdense, underdense regions become less underdense. So there is a natural expectation that starting from initial conditions like this, gravitational instability will lead to some kind of structure. Okay, so this of course does not tell you what kind of structure. You have to follow the physics to see what happens, and that is what people have done. But these are the initial conditions, and then you put it into the framework where I have gravity, which acts on dark matter as well as ordinary matter and radiation. And then you can set up a problem in which you write down equations that govern the densities and velocities of the dark matter and the baryons and the density of photons, and you can follow through on this. Okay, so if you do this, what will happen is that there will be an evolution. So for example, if you focus on the dark matter, there will be an evolution which leads to this gravitational instability that I was talking about. And one of the first people to recognize this and produce a very, very simple ansatz for what the fully nonlinear unstable solution of gravity should do was Zel'dovich in 1970. So what I'm showing you here is a realization of what is called the Zel'dovich Approximation. So let me see if I can play this image over and over. Okay, let's see from here. So this movie was made by Sujata, and what she did was to basically say, let's take the Zel'dovich approximation in which the velocities of particles are determined by the initial density perturbations that I was talking about. Okay, so the velocities of particles in this approximation are basically given by this solution, where I have two functions that I have to tell you. So Q is the location of the particle initially, and T is the time at which I am examining the solution. So the initial location of the particle tells me what velocity vector to assign to the particle initially by looking at the fluctuations in the initial density perturbations. So in the initial density field. So this, if you imagine, is the initial realization of a density field, density of matter. This density of matter drives gravity. So it creates a gravitational potential. That gravitational potential is psi. And if the density fluctuates, then so does the gravitational potential. Okay, and if you know how the density fluctuates, you can calculate what the gravitational potential should look like. So you do this at the initial time, according to Zel'dovich. And then you solve what is called linear perturbation theory. So I said that these perturbations are small, so you can write down Einstein's equations, for example, in general relativity, in the presence of small fluctuations, and solve the system. And that linear system will give you a solution which will determine this function f of t as a function of time. And what Zel'dovich pointed out is that just combining this linear solution with the initial conditions determined by the random field that I was talking about, will give you a good description of the velocities of particles starting from the initial time. And what Sujata did was to just evolve such particles forwards in time. And what you can see clearly is that as they evolve, they in fact start from a very homogeneous looking distribution and come to a system eventually which does have the same kind of filamentary network that we see in the observed data. So this is a very, very remarkable fact. It's a very simple solution, but it already has the power to explain, at least visually, what is happening in the real universe. Now, of course, you have to be very careful about such simple solutions. For example, it is already obvious just staring at it that this cannot be a full solution, because this is, as I've written here, straight line motion, in the sense that the vector direction of V is fixed by the initial conditions and it does not change with time. The only thing that changes with time in the solution is the magnitude of the vector. But of course, any student of Newtonian gravity will be able to tell you that the velocity of a particle changes both in general in magnitude as well as direction in the presence of a gravitational field. Just imagine throwing a piece of chalk up into the air and letting it go up and then come down. Not only does its magnitude change, at some point its direction also inverts. Okay? And the same thing with Keplerian orbits, etc. So these kind of effects are obviously not part of the Zel'dovich approximation, so it cannot be a full solution, but it does give us some very powerful insights into the evolution of large-scale structure, starting from these kind of tiny perturbations. So now people have gone ahead, and by now the field has progressed considerably. And what people currently do, and they have been doing for 20 years or so, or more than that, is to basically put this problem into a computer and run a computer simulation. So these are called n-body simulations, because you take n particles and you basically perturb their initial positions according to initial conditions that are constrained, for example, by the cosmic microwave background observations. And then you say that I will evolve these particles into the future using the equations of motion determined by, for example, general relativity, or in this case, at these scales, you get to use Newtonian dynamics. And you get these remarkable looking images from some of these simulations, which I have listed here. Sorry, I didn't give the links to these things, but you can easily look them up on Wikipedia. And you see that in all of these simulations, you can see this kind of cosmic web structure emerging. There is a filamentary network. The filaments meet in very overdense regions where you have gravitationally bound objects forming. Okay, so this is the focus of what I will be talking about. I just wanted to show you these couple of pictures here, and I just listed some of the names of these simulations that come to the top of my head. There are several more as well. So this is a very, very active field. So here is a simulation which we have run at IUCAA here some years ago, a couple of years ago. So there is nothing special about this simulation in this sense. It is just that it's good to have your own simulations when you work on large scale structures, so that sharing data, etc., is not an issue. And this is just a movie of the simulation. So what I have shown you is a slice through my box. The box is 200 megaparsec on a side. And the movie starts at a high redshift. It starts at redshift 12, and then this redshift, which is like a clock, it winds downwards. It comes down all the way to redshift 0. So redshift 12 is like a very early time in the history of the universe, something like maybe less than a gigayear after the Big Bang, less than that even, half a gigayear maybe. And redshift 0 corresponds to today, which is like 13 point something gigayears after the Big Bang. Okay, and what you see in the movie, it's just looping over and over in time, is that starting from relatively homogeneous initial conditions, this kind of filamentary structure evolves. So for example, focus on this region where there is this massive object forming. So the color is the density of dark matter in the simulation. This is a dark matter only simulation. So it's on a logarithmic scale. So blue is very underdense. And this red is at least 1,000 times overdense compared to the very deep blue. Okay, so this part is 1,000 times overdense compared to this part. So you can see a very dense structure evolving here. And you can see that it's a pretty complicated structure also. It is not just a simple spherical object. There is a lot of anisotropy and a lot of substructure that is surrounding it. There are several dense blobs. Some of them are merging, right? There is a merger happening right there. And this thing has become bigger. It's eating mass and it's becoming bigger and bigger. So classic gravitational instability. And on the other hand, if you focus on this region, when the movie loops over, you'll see that it also started from a relatively homogeneous looking thing, but it started losing all its mass to the surrounding overdense region. And it keeps getting emptier and emptier. Look at that. It's like a front which is moving forwards, right? And making this part emptier and emptier. And eventually this huge void forms in this region here. Okay, so this is in the standard lambda CDM cosmology, lambda cold dark matter with collisionless dark matter and Newtonian self-gravity. I'm happy to discuss all of these things if people are interested. What are the assumptions that go into simulations? What are the equations that are solved, etc., etc. Okay. So these movies are nice, but I also like to explain things using a series of cartoons. So the next few slides are just cartoon illustration of what we saw in the movies. Basically, this picture is called hierarchical structure formation. Hierarchical in the sense that there are tiny perturbations. These perturbations grow, and the first things to form are small objects. Okay, so the first kind of overdensity that you will see is a relatively tiny one. Then several of these small objects will come together and merge, like this one is forming here, and they will become one big object. And then that big object may eat up other equal size or smaller objects and become even bigger, and so on and so on. Okay, so this is hierarchical. There's a hierarchy of sizes and masses involved. And in this hierarchical framework, dark matter fluctuations grow under gravitational instability, and they clump and they form what are called dark matter halos. And these halos, they also grow and they merge. And eventually galaxies, which are the quantities that we see, these are the entities that we see in observations, they are believed to form in the deep potential wells which are created by these dark matter halos. So this is my representation of a galaxy, these yellow things. So some halos have galaxies, some halos may not have galaxies, depending on their mass. There is also a scatter. There is not a one-to-one relation between having or not having a galaxy. And then as structure progresses, as the evolution of the universe progresses, these halos can merge and become bigger. And the galaxies inside these halos will therefore form groups. And sometimes the galaxies, typically the galaxies tend to retain their individual identities. Sometimes the individual galaxies themselves can merge and become bigger, and so on. Okay, so this is the broad picture in which one works. And this has shown to be remarkably successful in explaining the broad properties of the observed cosmic web that I was showing you in the first few slides. So for example, for 100 years or so, we have known about the existence of large galaxy clusters. So these are not just groups of few objects. These are clusters of hundreds to thousands of objects. So these are a couple of famous clusters, the Abell cluster 2218 and the Virgo cluster, which have several hundreds to thousands of galaxies. Okay, and these have now been characterized in great detail. And for example, this paper talks about how to categorize the distribution of individual galaxies in the Sloan Digital Sky Survey into groups. So there was a group finding algorithm which they ran on these individual galaxies and their positions, and they have categorized objects into groups. So this is the kind of thing that people have been doing, and this is our understanding of how structure is organized in our universe. So here is a slide which gives you a few details of the kind of terminology that people use when discussing structure formation. So this is the cosmic web that I was showing you. This is from the Millennium simulation. And this is the zoom from the Millennium simulation onto individual objects that are forming in this cosmic web. So as I mentioned, these objects, they are called halos. So here is one halo in the simulation, in the Millennium simulation. Okay, and I just wanted to mention this, within the hierarchical structure formation framework, this is one of the pioneering papers which pointed out how one can understand the formation of this kind of filamentary network in the hierarchical paradigm, which is slightly different from what people were thinking of because of the influence of the Zel'dovich approximation. So remember, the Zel'dovich approximation just talked about straight line motion, and it produced something that looks like the cosmic web. Okay, and it was this paper which clarified how one can combine that original idea of Zel'dovich and place it in the framework of hierarchical structure formation, where small things form first and they grow and they merge to become larger. So basically what this paper pointed out is that the seeds of this filamentary network that you see are actually already present in the initial random field, which was very, very tiny perturbations, but the correlations in those perturbations already had the skeleton of this filamentary structure. Okay, so they wrote a Nature paper in which they demonstrated this. So it's a very interesting read, and I encourage all of you to look at it. I may have gotten the year wrong. I'm not entirely sure, in which case I apologize, but these are the authors. Okay, so here is a bunch of terminology for these individual objects. One characterizes these objects or halos by their mass, by their virial mass. They are expected to obey the virial theorem and be in virial equilibrium. This is an idea that goes back all the way to Zwicky, who applied the virial theorem to galaxy clusters. And they can be thought of in terms of their mass or their size, the virial radius, which is related to the mass using this equation, where this number, capital delta, is a number of order 300. And what one says is that the mass is the mass contained in a radius which encloses 300 times the mean density of the universe, roughly speaking. Similarly, there is the virial velocity or the circular velocity of an object, just in terms of its rotation curve. And the maximum of the circular velocity, which is the maximum of the rotation curve, this is called Vmax. So this mvir and Vmax are things that keep coming up. We will discuss them later also, so I thought I would write them down here. And you can write down, using these equations, some simple scaling relations to help you understand what are the typical sizes and scales involved in the universe. So for example, galaxy clusters are at the scales of 10 to the 15 solar masses. The Milky Way has a halo which is of the order of 10 to the 12 solar masses. Dwarf galaxies that we see in the vicinity of the Milky Way have masses of the order of 10 to the 9 solar masses. There's a very nice review from which I have stolen, in fact, some of these equations by Bullock and Boyle and Kolchin. It's a very nice read if you want to understand basic ideas in structure formation and the demography of halos and substructure, etc. Okay. So now let's get into a few slightly more technical things. So I think I'm doing okay with time. I'm about halfway through the talk. So what I want to focus on is the environments of such objects. See, the idea is these are the objects, these dark matter halos are the hosts of galaxies, which means the stage on which galaxy evolution and all the intricate astrophysics of galaxies is happening is provided by the potential wells of these dark matter halos. These dark matter halos themselves live in the cosmic web. And there is a hierarchy of correlations between large scales and small scales in the cosmic web, which was already laid down in the initial conditions, as Bond et al. Told us. So now it is an interesting question as to how these correlations across different length scales affect the evolution of individual objects and of the galaxies that live inside them. So this is one of the interesting questions for structure formation today. And the answers to this question are not only interesting for people studying galaxy evolution and small scale structures, they are also important for people studying cosmology, because we would like to, so as a cosmologist, one would like to use galaxies, for example, or other tracers as tracers of the overall cosmological, of the overall cosmology of the universe. So you would like to know, for example, what is the nature of dark energy? What is the nature of dark matter? These are fundamental questions which cannot be answered just on their own. They need to be answered using tracers of cosmology. So you need to understand what the tracers are in order to use them to do cosmology. So these questions have more widespread ramifications as well. Okay, so let's start by discussing two different kinds of environments that I would like to focus on. When people talk about environments of tracers, they can mean a variety of things. So I will be clear about what I mean by environment. So the first kind of environment I would like to discuss is the very large scale density environment, of halos. Okay, so what I mean is, imagine a halo like this. It's sitting at some place in the cosmic web. I would like to understand, if I put a huge sphere around this halo and I ask what is the total matter in the sphere divided by the total volume of that sphere, what does that density look like in comparison to the mean density of the universe? Is there something interesting I can talk about there? So this is an old idea. The large scale density environment of halos goes back to at least the mid 80s when it was discussed by Kaiser and BBKS, etc. And the way the discussion is usually framed is in the language of what is called a halo bias, where one says that the number density of halos of a certain mass. So if I go back here, if this is one halo, it has a certain mass. I go around in the simulation and I count all the halos which have similar mass, here, maybe somewhere else. I count all of them and I ask what is their number density and how is it correlated with the matter density around those halos. Okay, so I can ask this question, and it turns out that I can describe the result in a relatively simple manner, provided I'm talking about the matter density at very large scales. And it turns out that this very simple approximation, delta halo, is the fluctuation in the number density of these objects compared to their mean number density. Delta matter is the fluctuation in the matter density compared to the mean matter density. And it turns out that you can think of these two objects as being related by a simple linear relation at lowest order. And then there will be higher order corrections, and then other stuff will happen here. But this is a very simple approximation which seems to work reasonably well. And that is demonstrated here. So what is done here is to calculate what is called the power spectrum. So it's like saying I take delta halo, I take 2 powers of delta halo, and I do an average. So delta halo times delta halo averaged. I call that the halo-halo power spectrum. I do it in Fourier space rather than real space. So this is not x on the horizontal axis, it's the wave number k, which means that on the right-hand side, I have small scales. On the left-hand side, I have large scales, large length scales. And what I find here is that if I do this exercise for halos, and then I do the same exercise for matter, it's like taking 2 powers of matter, and then I take the ratio and I take the square root, this is the number I should be getting. And you see, in fact, that these quantities asymptote at very large scales to a pretty much constant value. Okay, and this constant value is called halo bias, linear halo bias in this case. And it has been very well studied in the literature, and there are fitting functions available for the dependence of this bias on properties of the halo, such as the mass of the halo and the redshift at which you identified the halo, and so on and so forth. Okay, so this is a very well studied quantity. It's called halo bias, but all it says is what is the large scale density environment of halos. What you see here is, think of the horizontal axis as the mass of the halo. It's basically a rescaled version of mass. What you see is that this halo bias is an increasing function of mass. So what one concludes is that at the same density, halos of a different mass will be clustered differently. Okay, so at the same if you hold large scale density fixed, halos of larger mass will actually be more strongly clustered than halos of lower mass. So this is a fact in simulations. So you might as well, you could just say, okay, I see it in simulations and I believe it. Or you could say, I don't believe it, I want to understand where it comes from. And in fact, this result goes back to well before N-body simulations were being performed. It goes back to Nick Kaiser in 1984, who gave a very simple explanation of why this kind of bias should in fact be an increasing function of mass. So this idea goes by the name of the peak background split, which I can explain later if someone is interested. But I just want to say that this is a reasonably well understood aspect of the density environment of halos at very large scales. So this is the important take home message. The scales that I'm talking about correspond to K values of what is this, right? So 0.05, 0.04, 0.03. So these are like several tens to 50 MPC scales in length. So very, very large scale density environments. The next kind of environment I want to talk about is a relatively local environment. So if I go back to this picture, what I was saying regarding halo bias will talk about this kind of scale, hundreds of MPC, 50 MPC. But now what I want to do is to zoom in on a halo. So this is 2 MPC here. So that means this is 2 MPC. So in fact, as it turns out, this kind of box, okay, which is roughly 8 MPC on the side, a few times the halo radius, this is exactly the kind of environment which I now want to focus on. So it's the small scale, but still external environment of the halo. So I want to understand now, what does the density field and other related quantities at this scale look like? And in particular, I want to focus on the tidal environment of these halos, because I know that one of the driving aspects of the physics at these scales is the gravitational potential. And the gravitational potential can be characterized by its second derivatives. So of course, its value also tells you something, but what is more interesting is the second derivatives, the tensor of second derivatives, which is called the tidal tensor. So for example, if I take the trace of this tensor, I get the Laplacian of the potential, which obeys the Poisson equation. And this delta is the same as the delta that I have been talking about. It's the fluctuation in the matter density contrast, in the matter density. So now I want to go beyond the matter density, and I want to talk about this tidal tensor. So I've tried to show you what this tidal tensor does. In particular, what I want to focus on is the anisotropy of the tidal environment. So I want to go beyond density, which is a spherically averaged quantity. And I want to characterize how anisotropic is the region around such a halo. Okay, so I could put down spheres here and I will calculate a spherically averaged density. But you can clearly see already here that there is an anisotropy in the system. This direction is clearly different from this direction. I hope my cursor is visible. Okay, and I want to characterize this anisotropy. So the tidal tensor gives you one way of doing it. There are other ways as well, but I want to focus on this because it turns out this is an interesting thing to do. So what does one do? This is a tensor in 3 dimensions. So I can diagonalize it. It's a symmetric tensor, real. So I can diagonalize it. I get 3 eigenvalues. And in the literature, you will find that people will use the ordering of these eigenvalues and how many of them are positive or negative. They will use this information to classify every location in space as being part of what can be called node, filament, sheet, or void. Okay, so a node is a place which is very, very dense and where all 3 eigenvalues are positive. So a node is a place like this, where stuff will fall in along all directions. A filament, on the other hand, has 1 eigenvalue which is negative and the other 2 are positive. So it's a place where along 2 directions I will have infall, and along the 3rd direction, I may have outflow. So imagine a filament that does this here, okay? So along the direction of the filament, I may have a flow pattern which goes towards the joining nodes, but perpendicular to the filament, I may have infall. Okay, and this can be characterized by looking at the number of eigenvalues of the tidal tensor. So this kind of classification exists in the literature, and what we were interested in is to go beyond this and have a continuous classification of the anisotropy of the tidal environment. So you can clearly see that a node is going to be relatively isotropic because it's going to pull things in from all directions. A filament is clearly anisotropic because it along one direction there is an anisotropy, and so on. So what we argued is that there is a particular scalar quantity that you can construct out of these eigenvalues, lambda 1, 2, and 3, which is defined here. And it turns out to be a useful scalar description of the anisotropy of the environment, in the sense that if this alpha is small, then your environment is very isotropic, because what you can see from here is that this alpha is constructed out of this quantity, which has differences of eigenvalues appearing. So remember that if I have an isotropic tensor, all 3 eigenvalues will be equal. So this quantity Q will be 0 and hence alpha will be 0. Okay, so small values of alpha will mean very isotropic environments. And correspondingly, if I have very different eigenvalues, then I will get a large value of alpha, and that large value will correspond to anisotropic environments. And what the other important variable is delta itself, okay, smooth on the same scale. And this is just the sum of the eigenvalues. So what I've tried to show here is what would happen if I fix my delta and I just change my alpha. Okay, so my anisotropy alpha is different. It's small here and large here. And I've tried to show you what flow patterns would emerge for an initial ring of two-dimensional distribution. And what you see is that if I fix my delta, then in the case of small alpha, I will have an ellipse that looks like this. Whereas in the case of large alpha, I will have a much more flattened ellipse. Okay, so this is a more isotropic environment than this, according to this variable alpha. So this is what I want to do, and I want to apply to n-body simulations to individual halos. So I want to see for individual halos, what does this quantity look like? And I want to see what does this large scale density environment also look like? So that is what is shown in this movie. Both panels show you the same halos running forwards in time. The colored points are individual halos in the simulation. The color of the individual points is the tidal anisotropy alpha in this panel and the large scale halo bias in this panel. So remember, small anisotropy is isotropic environments. Large anisotropy is anisotropic environments. So red colors in this panel are isotropic environments. Blue colors here are anisotropic environments. So let's focus on the left panel and see what's happening. You can see that in places where there are not many objects, the points tend to be red. Okay, so all of these points are red. And here, these points are all blue, and they are very clearly, visually tracing out these filaments that are forming in the large scale structure. Okay. So this is a nice visual demonstration that is alpha is doing what it was intended to do. It is tracing out the anisotropy of large scale structure by pinpointing the places where the large scale structure is very anisotropic in the tidal environment and where it is very isotropic. And this alpha is defined at a scale of a few times the halo size, like the picture that was shown here. Okay, so these are the scales at which alpha is defined. And in the right panel, which I will now focus on, I'm talking about scales which are much larger, several tens to 100 MPC. That is here. So here, what I have done is to color the same halos by their large scale bias. This was measured at very large scale environments. And here what you see is that the pattern of color is very different. So here large value means a large density, small values means a large overdensity. So for example, you can see that here in the same place where you had very isotropic environments, you also tend to have very blue colors here, which are very underdense regions. Okay, so this is completely clear, right? Because this is a very underdense region. So not surprisingly, the large scale density environment has a large negative value here. And correspondingly, in this case, there is a lot of objects forming here and moving in closer. And therefore you see very red values here, okay? The point being that this pattern of color is very different from this pattern of color, which means that this statistic as a tracer of environment is doing something very different from this statistic as a tracer of environment. So let me halt the movies so you can focus on the differences in color. So this statistic, which is defined at a few scales of a few times halo size, is more interested in what the filaments are doing. Whereas this one is more interested in what the overall spherically average large scale structure is doing. Okay. All right. So this is one aspect of these environmental variables. And this is focused on small halos. Okay. So the halos that I colored for you here are all small halos in the simulation. This movie, the next one, this one, shows you the same slice again. But now I have chosen to color the large halos in the simulation box in the same slice. And now what you see is something completely different. Okay, so for the bias, you see something very similar to before. In this region, you have reddish colors, and in these regions, you have bluish colors. The main difference you will see is that these massive objects don't live in these underdense regions. Okay, and there is a very nice reason for this, which I can discuss later. But apart from this striking difference, there is not much difference between this panel and the previous slides panel, the right-hand panel. But here you see something completely different. Let me halt the movie again. So here you see something very different as regards the large scale structure. So remember in this one, this same region had a lot of small objects which are very blue. On the other hand, if I go here, the same region has a single massive object which is very red. And actually, if you think about it, it is very clear why this must happen, because this alpha is always defined at a few times the halo size. So this is a monster object which is forming in this region in the simulation box. Okay, and the environment of this massive object at a size which is slightly larger than this massive object is completely dominated by the presence of this object. So this environment, as far as you focus on this object, will be very isotropic, because this object dominates its environment. It basically makes all regions around it the same. Okay, it is the thing which is pulling everything towards it. But on the other hand, these tiny objects which are living in the vicinity of this large object, they see the environment determined by this massive object. The gravitational potential is dominated by this guy. So they see a very anisotropic region in the tiny regions around them. Okay, so that's why these guys are blue. They see very anisotropic environments, whereas this massive guy sees a very isotropic environment. So that is another reason why this variable alpha is very interesting. It naturally captures the multi-scale cosmic web environment of objects. Okay, so this aspect is very interesting and useful. And on the other hand, the large scale bias does something relatively less subtle. It just does things which are intuitively very easy to understand. Places where there are many halos will have a large overdensity, very similar for both masses, and where there are fewer halos will have a larger underdensity. Okay, good. So these are the environments of objects. Now what we would like to discuss are correlations between properties of halos and the large scale environment, because this is the thing that we slowly want to get to. What are the properties of eventually of galaxies, but first of halos, which live in different kinds of environments? So this has also been studied quite a lot in the literature. And like I showed you earlier, one of the primary variables that has determined in the past the environment of an object is the mass of the object. So for example, in this plot, we saw the large scale density environment as captured by halo bias as a function of the mass of this object. Okay, and we saw that the large scale bias is a relatively strong function of the halo mass. So the mass of an object has always been traditionally the main environmental driver of all properties of the object. And the reason is not difficult to understand, because if you look at this equation, what you see is that the density enclosed inside a gravitationally bound object is of the order of 300 times the mean density of the universe. Okay, so now if I ask the question, consider some halo which has formed not exactly at the node of the cosmic web, but somewhere in this filament. Okay, let me see if I can show you a better zoom. I can show you my simulation one. Okay, this one. So let's take an object which has formed in one of these fat filaments here. And let's ask the question, the halo that is forming here, would its environment be, would its properties be determined by its local density environment or its large scale density environment, or would they be better determined by the fact that it is sitting in a filament? So let me put it in a slightly different way, focusing on even smaller scales. Suppose I have a galaxy sitting in this halo, and I ask the question, do the properties of the galaxy sitting inside this halo depend on where the halo is sitting, or do they depend mostly on how big the halo is? Because this is a question that you can ask. And it turns out that for most practical purposes, you can simply say, give me the mass of the halo, and then I will tell you what the galaxy in such a massive halo should look like. Should it be luminous? Should it be faint? Should it be red? Should it be blue? Most of these properties can be determined knowing just the mass of the halo. Okay, this is something that has emerged from studies of structure formation, and it seems to be a reasonable description of the distribution of galaxies today. But there is an equally interesting question whether the mass of the halo is the only important thing, or whether such a halo being in a filament versus being not in a filament makes a difference. Okay, so this halo is clearly in a very overdense region, It is in this fat kind of filamentary structure here. This halo looks reasonably as massive as this guy, but it is not in the middle of a filament. It is probably sitting, it is probably sitting at the node of a filament. Okay, so these kind of questions people have asked. And because this overdensity that we are talking about is very large, it seems to make sense that it is the mass of the halo and it is the density environment of the halo itself, which must be the primary driver for galaxy properties, rather than whether the halo is sitting in a filament or not, because the filament will have a much lower total overdensity of the orders of tens rather than hundreds. So these kind of questions people have asked, namely whether properties of halos and the galaxies inside them respond to more than the halo mass. So this kind of idea goes by the name of assembly bias. I have not listed all the references that talk about this. It's a very, very wide topic now. It started a little bit before, around 2004. I'm showing papers, I'm showing results from this paper because they are relevant to what I want to discuss. Basically, what the conclusion is that halos that tend to be younger, that tend to have formed more recently, they tend to cluster less than halos that are older, that have formed relatively earlier in the history of the evolution at the same halo mass. Meaning today I take a halo of similar mass, for example, here and here. This is taken from this paper. And I segregate these halos by when they accreted most of their mass. So in this case, this halo has accreted most of its mass relatively recently. It is still accreting. And in this particular case, the halo accreted most of its mass long ago, and it is currently not accreting any mass. And the consensus that has emerged is that halos of this kind, which are still accreting, they tend to be less clustered. So what is shown is the clustering strength, similar to the halo bias, if you like, but now as a function of scale. This is the 2-point correlation function, not the power spectrum. And halos that are younger cluster less strongly than halos that are older, for halos of a relatively small mass range. Okay, so these kind of assembly bias trends are interesting. I will not discuss all the details of this plot currently for lack of time, but you can ask me about these things later if you're interested. What we would like to understand are whether these assembly bias trends can tell us, are telling us something interesting about galaxy evolution eventually, and what they are telling us about structure formation in general. So more recently, we have been exploring these assembly bias trends in a little more detail using these two variables that I was talking about, the tidal anisotropy and the halo bias. Let me remind you. So the tidal anisotropy looks like this or this, these blues and reds, and the halo bias looks like this. Okay, so what we wanted to do is to understand the nature of halo bias, not just as a function of halo mass, but also as a function of this tidal anisotropy strength. And what we find is that halo bias is a fairly strong function of tidal anisotropy. So what you can see here, for example, is the typical bias of halos at fixed mass, but split by whether those halos have a large anisotropy or a small anisotropy. Okay, and you can see that as I increase my anisotropy, as I go from reddish colors to bluish colors, color scheme is the same as in the previous panels, you go from low bias objects to high bias objects. And this change, going from low alpha to high alpha, taking you from low to high bias, this relative change is much stronger than the change that you get going from low mass to high mass. Okay, it's a fairly quick change here, whereas here you have to wait for like 2 orders of magnitude in mass until you get a similar change in the value of halo bias. So alpha is a pretty strong indicator of halo bias. And this is interesting because now you get to, and this is a plot, for example, from a recent paper by Sujata, which shows that this result is not just restricted to linear halo bias. You can extend it to quadratic halo bias and you see similar trends. Alpha is a pretty strong indicator of nonlinear halo bias as well. So now this is interesting because you can ask the question, this alpha is defined at a relatively small scale compared to the size of the halo. So it has a better chance of being correlated with internal halo properties. And those internal halo properties in turn are probably correlated with galaxy properties. Okay, so it is interesting to ask then whether alpha can tell us something interesting about internal halo properties. So this is something that Sujata did a couple of years ago, which showed something very interesting. So in the middle panel here, I'm showing you what I was calling assembly bias in the previous panels, but now shown in a compact manner by calculating a correlation coefficient. Okay, so what one can do, I will go back again to this plot, for example. So here I have shown the halo bias of every single object as a scatter plot against halo mass. But now you can imagine doing this exercise against any other variable. So for example, I can take a narrow bin of halo mass. And in that narrow bin, I can take a scatter plot between halo bias and some other variable like alpha, for example, or some other halo property. So for example, I could take the formation time of halos as my second halo property in a narrow bin of halo mass. And I can calculate the bias and this second property for each object. And I can calculate a correlation coefficient between them, which measures the strength of the correlation between these variables. So that is what is plotted here. There's a rank correlation coefficient, which is computed. If it is positive, it means that these are positively correlated. So if I increase the value of halo bias, I will increase the value of that property or vice versa. And if it's negatively correlated, it means that if I increase one, I will decrease the other, and so on. So what Sujata did here was to calculate the correlation coefficient between halo bias and a bunch of different halo properties, which have been studied in the literature. So for example, if you think about formation time, the one that comes closest in the one that we studied is this CVIR, which is the halo concentration, which is a rough proxy of formation time. Not a good proxy, but a rough proxy. Similarly, there are other properties like the spin of the halo, the shape of the halo, and the velocity structure of the halo. These are these variables. I can define them in more detail later. But the point is, these are variables that have all been studied in the literature, and their large-scale bias trends have been studied. And this plot summarizes all of these trends. These are all known trends from the literature. For example, we see the trend that bias versus concentration or formation time has this interesting feature that at large halo mass, there is a negative correlation, and at low halo mass, there is a positive correlation. And for halo shape, for example, there is always a positive correlation. So halo shape in this case is the ratio of eigenvalues of the mass tensor of the halo. So if this ratio is close to 1, then the halo is spherical. If the ratio is close to 0, the halo is very aspherical. So large values mean spherical halos, small values means aspherical halos. So what this is saying is that spherical halos tend to be more clustered than aspherical halos. Okay, all right. This panel shows you correlations between all of these properties and the tidal environment alpha that we talked about. Okay, the same properties, but now correlated with alpha. And additionally, the correlation between alpha and bias, which we already saw in this plot in a different way. So you saw that as I increase alpha, I increase halo bias, which you see again here. There is a positive correlation between these. But the interesting thing that you see is that all of these other properties are correlated with alpha in basically the same way as they are correlated with halo bias. All that happens is that the strength of the correlation is very different. So notice the y-axis scale here is very different from the y-axis scale here. These correlations are all much weaker than these correlations, but visually they look identical. This one is very flat, this one is going from negative to positive, this one is increasing, etc. And this is what made us realize that you can do the following statistical analysis. You can ask, can I explain the correlation between, let's say, beta and B1 by arguing that actually beta and B1 are not fundamentally correlated. What is fundamentally correlated is alpha and B1 and alpha and beta. Okay. So can I make this argument? Can I explain the correlation between beta and B1 as fundamentally arising from the fact that these two variables are both correlated with alpha? And statistically, you can frame this question by calculating what is called a conditional correlation coefficient. There's a particular formula that you use. Basically, you use the purple points here, the red points here, and the red points here. You combine them in a certain way. You calculate a conditional correlation coefficient. If this conditional correlation coefficient vanishes, then you can argue that the correlation between B1 and beta is not fundamental. It is determined by the correlation between B1 and alpha and beta and alpha. And the remarkable thing that we found was that for all of these variables, it looks like this is indeed the case. Okay, it's within errors, most of these variables seem to have conditional correlation coefficients, which are pretty close to zero compared to their original correlation coefficients. So this was a pretty interesting result, that all of the, or most of the correlations between halo properties and large scale structure, what people have been calling assembly bias, can basically be explained by a single variable, which is the tidal anisotropy alpha, defined at scales of a few times the virial radius. Okay, so this is as far as I wanted to say about halos. Okay, so I am basically out of time. Marcello, you should tell me how much time I can take.
I think, well, you are 5 minutes over time, but maybe you started a bit later. So yeah, you can have 5 minutes more.
What I will do is I will try to wrap up quickly.
Yeah.
Okay, so all I wanted to say is that this is all fine, and it's great that we understand this for dark matter halos. It has given us several insights into structure formation, etc. But at the end, what you want to really understand are what galaxies are doing. Okay, so you want to go from dark to light. I will not talk about exactly how one does this. I will just jump to what I want to discuss, which is interesting for me. Which is, okay, so let's say that we take the best prescription that we know of currently, which is doing a hydrodynamical simulation with a bunch of physical models for star formation and the effect of gas and metals, etc., etc. And you ask people who are experts in this, for example, the Illustrious Collaboration, to share their products with you. They have made their products publicly available. So you can go and you can take the galaxies that have been produced in these simulations, and you can ask, what are the correlations between the properties of these galaxies and the structure in the universe and the large scale structure of these simulations, the cosmic web in these simulations. And here what we have found is something very interesting, which is that if you take this tidal anisotropy variable that I was talking about, it is a slightly modified version of this tidal anisotropy, which we call alpha peak. It's the maximum of the tidal anisotropy over a accretion history of an object. This particular variable turns out to be a very interesting indicator of star formation properties in such galaxies, in these simulated galaxies at least. And what is shown here is a slice from the illustrious TNG simulation. I will not go into details, but basically you can see the cosmic web of the TNG simulation. This is the density of matter in the simulation in the color scale. And here you see the anisotropy of the tidal environment in the illustrious TNG. And the colors here are the tidal anisotropy, whatever I have been discussing, of individual galaxies, which are the points. And the colors in this panel now are the star formation rate of these galaxies. And what you can take away from this panel, or from this slide, is that wherever I see blue colors here, meaning anisotropic environments, I tend to see red colors here, which means less star formation. And correspondingly, wherever I see yellow-orange colors here, like these regions here, these are relatively isotropic environments. Here I see correspondingly blue colors, which are relatively highly star-forming regions. So what we realized is that the tidal anisotropy correlates with star formation activity. So here I'm showing the star formation rate and the stellar masses of these objects in the illustrious simulation, colored by their typical value of tidal anisotropy. And what you see is that for objects which are not star forming, focus on objects that happen to the left of this line. These are small objects, the ones that I colored here. Okay, so they all lie in these rectangles here. Imagine this is halo mass. Okay, it's measured in velocity units. It's like circular velocity, but this is a proxy for halo mass. So I'm talking about small objects. And in these small objects, if I look at highly star forming objects, which are up here, vertical axis up here, I see that the tidal anisotropy tends to be low compared to objects that are down here, which are not star forming, and their tidal anisotropy tends to be very high. So this is a very interesting correlation because it not only extends from star forming to not star forming objects, it also extends from what are called centrals to satellite objects. And traditionally, central and satellite objects have been thought to be very different. They have been thought to have very different physical processes happening on them, and they are physically different entities, etc. And what we are finding is that actually the distinction between star forming and not star forming, and the distinction between centrals and satellites is actually all governed by the value of this alpha peak, okay, the value of the tidal anisotropy. For example, it also explains, let me not go into too many details here, but basically we think that it explains the probability that a galaxy is not star forming. This is the fraction of galaxies that are quenched. We believe that we have demonstrated that this probability or this quench fraction is essentially determined by the value of this alpha peak. It does not really depend on whether the satellite is classified as a central or a satellite. All that matters is that the most extreme tidal environment that this galaxy has encountered is a certain value. Okay, so this most extreme tidal environment seems to be the primary indicator for star formation of galaxies. So let me not talk too much about this. Let me summarize. What I have tried to say is that the cosmic web on its own is, of course, a very striking feature, and it therefore deserves understanding on its just by the fact that it exists. It has been studied for many years, and its role in shaping galaxy evolution has until now been kind of not very clear. So this is something I skipped. But basically, what we have believed until now is that the properties of galaxies inside individual halos are essentially determined by the halo itself, not really by whether the halo is in a filament or in a void, etc. And this picture is now being updated. And a lot of people have worked on this. I have not shown you all results by everybody in the literature. I focus on my own results, which seem to indicate that the properties of galaxies seem to respond pretty sensitively to the tidal history of this galaxy, even at fixed halo mass, essentially. And therefore, this leads to several interesting questions, which we are now exploring. For example, if you want to empirically model the distribution of galaxies using abundance matching, etc., there are some interesting lines of approach that we are now thinking about. So I will stop here. Sorry for going over time, and I'm happy to take questions.
So yeah, thank you very much. Very interesting. So yeah, if there are questions in the audience. Question, okay, maybe how do, so there is a question.
Okay.
Yeah, I can probably.
And it's not better to organize by raising hands, but people can just speak up. I think they're not so.
Yeah, exactly. And so, yeah, Ubina, do you want to ask your questions?
Yes, thank you. Thanks for the talk. That was fantastic. So I have two questions. Yes. One should be a comment on a paper, and the other one, I think I should ask that first. Was wondering whether you have a fitting function for the halo mass function that includes the tidal effect, the tidal history that you described.
Interesting. Yeah, and I see what you mean.
Sorry, the second question is comment on, that was a paper that appeared, I think, in April this year by Will Percival and collaborators, where they claim to have detected the assembly bias in BOS DR12 from
right.
From your work, it appears to show that there is really, maybe they dictated some tidal.
Right. So you're probably talking about Andrei Obulian's work?
Yes, right? Yes, yeah.
Yeah. No, I know the paper. That's right. So I think assembly bias has had a very checkered history because for every paper that you find that detects assembly bias, there is a paper which says that they cannot detect assembly bias. So I think the other issue is that different people mean different things by assembly bias. So in this context, what I would argue is that until now, it has not really been necessary to think of specific star formation rate being correlated with halo environment beyond halo mass. So in the following sense, suppose I take the results of SDSS clustering, the legacy results of Zehavi et al. Or Go et al. 2015. The modeling that they do, which gives an excellent description of the clustering, the luminosity and color dependent clustering of Sloan galaxies, does not require these galaxy properties to be determined by anything other than halo mass. Okay, so now you can come up with a specific, so I think this is what I've now forgotten the details of Andre's paper, but you have to be a little bit careful as to what question you're asking. And for the question that I am asking, I think this kind of physical insight has been firstly completely lacking, because we have not needed in the data to introduce additional correlations between something like specific star formation rate and halo bias. But at least in the simulations, it seems clear now that the effect is there, and it has probably been hidden by the fact that one treats centrals and satellites separately in all the modeling exercises. Okay, so this is the thing that that I did not get time to discuss. I don't know if that answers.
Yes, it does. And the first one, the fitting function question.
Oh yes, so you are talking about this plot. I do not have fitting functions for this. We did not focus on this. What we do have are fitting functions now from Sujata's recent paper, which is cited here, for the linear and quadratic halo bias as a function of alpha. But these mass functions are not there yet. I agree, it may be interesting, but this is a slightly more complex exercise. But we can discuss. I mean, if you're interested, I can always share this data with you, right? Okay. Or if you have access to other simulations, I can share code snippets which tell you how to calculate alpha. It's completely straightforward. You need an access to the snapshots of the simulation. That's the main requirement. And you can do it in whichever simulation you like as well. Or I can share this data as well. That's
definitely, I would send you.
Yeah, just get in touch with me over email and we can take it forward.
Okay, thank you. Thanks.
Yeah.
Thank you. So there is another question request. Calvin Stuma.
Yes.
Hello. Yes.
Yes. Thank you very much for the wonderful talk. I think my question is general question on the dark matter halos. Is there any way in which the dark matter halos could help the scientists to find the missing force in the universe?
The missing force in the universe. What do you mean by missing force?
Missing mass. This unknown mass.
Yes. So I think what one means by dark matter is what typically one used to call missing mass. But there is a slight potential for confusion here, because within the dark matter paradigm itself, there is what some people call the missing baryon problem. But this is basically an observational issue, that we know that the amount of ordinary matter in the universe should be something, but the amount that we can observe and account for is less than that. But that is primarily because it is very difficult to observe ordinary matter in all of its phases. Okay, because it depends on how hot it is and whether or not it is emitting light in the wavelengths that we can receive, and whether it is emitting enough light, etc. So if you're asking about missing baryons, that is an observational issue which hopefully will get sorted out as observations become more and more sensitive. But if you're talking about missing mass in the classical sense, in the sense that people were talking about in the last century, I think this is what one means by dark matter. So what people are now doing, of course, we have not detected the actual particle or the high energy quantity which forms dark matter. We have not detected it in the lab, but astrophysics and cosmology have allowed us to map out the effects of dark matter and to make statements like in this region of space, we can say that the dark matter density must be this and this. Yeah, so in that sense, one has detected the effects of dark matter. We have not really detected dark matter, but we have definitely observed its effects. And using these effects, we can then argue that the amount of dark matter that must be there must be something. Okay, and that is how one builds up the energy budget of the universe.
Okay, last question. Does the mass of the dark matter affect the object within the halo?
You mean the mass of the dark matter halo or the mass of the dark matter particle?
Or like something like maybe the particles affecting maybe the object within the halo. Is there any way in which?
Okay, so I'll try to answer in a couple of different ways. So first of all, there is the mass of this gravitationally bound object itself, which you see here. So
Yes.
meaning if I put a circle here and I count all the mass inside, that will be some value, right? And you can ask the question, if there is a galaxy sitting right at the middle of the object, will the properties of the galaxy depend on all the mass, the value of the mass that I counted? And that answer is yes. Okay, so the answer is yes. For massive objects, the galaxy sitting inside would have had access to more fuel for producing stars. So the galaxy would also be more massive on its own. It would be brighter. Yeah, so more massive halos will tend to have more bright galaxies sitting inside them. And also, if it is a massive object, what will typically happen is that the galaxy right at the center would have gone through a lot of interactions in the past, etc. And its star formation activity might be switched off currently. Okay, so the galaxy might be both very luminous and also quenched. So the properties of the galaxy do depend on the mass of the halo. There is another way in which you can think of this question. You can ask the question, what is the mass of the particle that is forming dark matter? And whether that makes any difference. And there are very interesting consequences, because the mass of that particle, which is a microscopic mass, it can determine the correlations at large scales between these dark matter fluctuations. Okay, it can tend to wipe out or not wipe out correlations at large scales, depending on whether this mass is large or small. So low mass dark matter particles, what is called warm dark matter, could in principle lead to a very different kind of structure formation in the universe. So people are also interested in asking such questions.
Thank you.
Yep.
Okay, thanks. So there is one other question, which from Buhafs Fares from Algeria. So he asks if there is a relation between halos and supermassive black holes and the galaxy formation. I guess, yeah,
Yes.
I think, yeah,
yes.
you can
Okay.
probably comment
Great.
about feedback.
Yeah, that's right. So, okay, so one of the issues is, so we know that there is a tight correlation between the mass of the supermassive black hole. So first of all, I think the general consensus is that basically every galaxy has a supermassive black hole at its center. Now, there is also a very strong observed correlation between the properties of this galaxy, of each galaxy, and the mass of the supermassive black hole. Okay, there's a tight correlation between velocity structure of the galaxy and the black hole mass. There is, when you ask whether there is a direct physical connection between the mass of the halo and the mass of the supermassive black hole, this becomes a little more complex, because the scales, the length scales involved are firstly very different. So the supermassive black hole is at, parsec scales, right? The galaxy is an object of size kiloparsecs, and the halo can be an object of size hundreds of kiloparsecs to a megaparsec. So the length scales involved are very large, very different, and therefore it is difficult to imagine a direct physical connection between whether or not a halo is doing something, rotating this way or that way, collecting mass, and what is happening to that tiny supermassive black hole at its center. So most likely the physical drivers are the connection between the black hole and the galaxy surrounding that black hole. Okay. Now, having said that, let's come to what Marcello was referring to. If there is a supermassive black hole, people believe, at least in the very massive objects, that this black hole can drive jets in the interstellar medium of the galaxy surrounding it. And maybe these jets can also be so powerful that they drive matter into the intergalactic medium or the intra-cluster medium of the surrounding galaxies. Okay, so these are now not the observational evidence for such large-scale jets on a sustained basis is not secure. But it turns out that these kind of effects are definitely needed in simulations, without which the simulations cannot reproduce other observed quantities like the luminosity function of galaxies. So the general consensus is that something like this kind of feedback mechanism, where a black hole switches on, it pushes a jet, the jet drives matter and momentum, it maybe heats up stuff around it in the matter outside the galaxy also, right? And it maybe drives actual matter physically away from this galaxy into the medium. These kind of effects can affect the star formation properties of such a galaxy. And this kind of thing is called AGN feedback. There are also even more speculative things where this kind of effect might drive the star formation activity of other galaxies. That is even more kind of exotic to imagine. But people are wondering about such things because we see some interesting correlations in the observations, which are turning out to be difficult to explain otherwise. So it's an open field. I don't think there is a final word on AGN feedback and its effects and its observational constraints, but a lot of people are working on this. Yes.
Okay, thank you. So I have one question too. So you seem to be saying that at equal anisotropy, so if two halos have the same value of alpha and the same value of delta, then they behave in the same way regardless of whether they are in a filament or they are satellites in a node. Is that true? Or?
You mean with respect to the to this stuff that I was talking about with the galaxies?
Yeah. So well, yeah. So that okay. So I remember you showed the plot where galaxies had the halos had the same color, so the same alpha values, whether regardless of whether they're in a node as satellites or in a filament. And then I was wondering whether these also has.
Yes. So, okay. So I think what we are starting to see is that, so of course you can define you can characterize the cosmic web in different ways and at different scales. So the question for us is, which is the most useful characterization as far as galaxy properties are concerned? So you could always ask the question whether, if I have a filament which is defined as a cylinder of size 30 MPC in length and 10 MPC in width, and I embed a halo here of mass 10 to the 11 versus I embed a halo somewhere else, whether I can see differences. So I would say that for galaxy evolution, it seems that the tidal anisotropy at roughly 4 times the halo size is the main variable that matters. As long as this variable, and it will typically happen that a large value of alpha will typically be, and the object will typically be in a fat filament near a massive object. And a slightly lower value of alpha will take you maybe in the middle of a filament, roughly alpha of half or so. And an even lower value of alpha, less than 0.2 or so, will take you into a void. So this correlation will definitely be there. So I'm not sure then
so you cannot,
what else you would like to use to characterize being in a filament or not.
Okay. So you're saying, so maybe then I got it wrong. So you're saying that if you have different values of alpha, you are likely to be in different environments.
Yes.
It cannot be like a satellite in a node or
so if you have a high alpha, then you're not going to be at a node for sure.
Okay.
So sorry, I didn't show that plot. In our paper, we have a plot where we show the distribution of alpha and we color traditional nodes and traditional filaments with different colors. And you can see that there is a sharp distinction. Low alpha is nodes, high alpha is filaments.
Okay.
There's like almost a vertical
bimodal, yeah,
exactly. Yeah.
Okay, so I think we had a fair amount of questions. I don't see any more questions coming up? Anyway, Aseem is, I think, available to answer questions. If you want to write to him, he will,
feel free. Please,
he can also reply by email. So I think thank you. I will thank everyone for coming. So, and of course, I will thank Aseem for this nice presentation.
Thank you for the invitation.
Okay. Yeah. All right.
All right.
So thank you very much.
Bye, everyone.
Have a good day. Bye, everyone. And of course, the recording will be available on the YouTube channel of the Institute in some time. Thank you.
Bye.
Bye-bye.